Hi, this is Eric and welcome back to Math from the Gut. In this section, we consider what happens to h, the length of the hypotenuse when one of our legs, x or y, gets longer. If h always increases when x and or y increase, then we can say that h is monotonic with respect to x and y. A simple example of monotonicity is money and apples. You can see that as you spend more money on the left, you get more apples on the right. The more money you spend, the more apples you get. The less money that you spend, the less apples that you get. So we can technically say that the number of apples you get is monotonic with respect to the amount of money that you spend. Let's start with our classic 5, 12, 13 right triangle. To keep track of things, let's trace over our starting hypotenuse with this dotted red line. For this test drive, let's consider what happens to h, the length of our hypotenuse, when x gets longer, but y stays the same. For example, when we increase x from 12 to 16, the triangle grows like this. When we do this, does our new hypotenuse look like it's gotten longer? In other words, does it seem longer than our red dotted hypotenuse from before? One way to think about this is to picture a rubber band stretched between our two red dots. If we now want the upper side of this rubber band to reach our blue dot instead, do we have to stretch the rubber band tighter to get there? If so, then our distance is longer. I'm hoping you can see that making x longer also makes h longer. Again, a fancy way to say this is that h is monotonic with respect to x. In other words, the length of the hypotenuse always increases when x increases. We can also show this another way with circles, and to do this, we'll take a quick trip to the lake. Let's say that blue circle is our lake and that all the green area outside of it is trees and grass. Let's also say that you're standing on a small island in the middle of the lake, right here. And let's pretend that the lake has a radius of 100 feet. This means that you need to swim 100 feet to get from this island to here. Like this. Now, let's say you want to go here instead. Rather than going only left to right, we would have to swim in this direction. The distance, however, is still 100 feet since we're still on the circle. Same thing for this point. Same 100 feet. Hopefully you can see that all points on the circle are 100 feet from the center. That's what makes it a circle. A radius line is always 100 feet. Now, let's say we see a beautiful flower in the lake right here and want to go get it. Do we need to swim more than 100 feet or less? Let's see. We would need to swim along this line. If we then swam this extra distance in the same direction, we would eventually go a total of 100 feet and reach the edge. But we didn't have to go that whole 100 feet that included our extra distance to reach our flower. Therefore, I hope you can see that we swam less than 100 feet. In general, we never have to swim more than 100 feet to reach a point in the lake when we start at the center. Now what about this point in the woods over here on the left, where we left our picnic basket? Is that more than 100 feet from our island? Well, to get to it, we need to first swim in this direction to reach the edge. How far did we swim? Well, 100 feet, since that's the distance to reach the edge of the lake in any direction. But we're not done yet. We still need to go this extra distance to reach the basket. Therefore, our total distance from our island to the basket must be more than 100 feet. In general, any point outside of the lake will be more than 100 feet from our island at the center of the lake. So, back to our original triangle. Let's create a circle around the lower left point. Let's make its radius equal to the length of our hypotenuse, like this. Now, let's fill it in and pretend that it's just like the lake from before. So remember, using what we just learned, we know that any point outside of this blue circle is more than 13 units away from its center. In other words, from this left-hand point on the triangle. Just like before, let x get bigger while y stays the same. But this time, watch how the blue dot moves on the top of the triangle. Here it is again. Notice how this blue dot immediately goes outside the circle once the triangle starts growing. It's just like our picnic basket being outside of the lake. This means that, right away, our hypotenuse is longer than 13 once the triangle starts growing. And, of course, it's also longer than 13 once x has reached a length of 16. So, this is another way of seeing that our hypotenuse gets longer as x increases. In this next slide, we see what happens when y gets longer as x stays the same. In this case, y changes from 5 to 9. Watch this. Here it is again. Again, our blue dot, which traces out the far end of our changing hypotenuse, immediately goes outside of the circle. This means that the length of our hypotenuse immediately becomes greater than 13 once our triangle starts growing. And h is clearly greater than 13 since we also end up outside of the circle. Now, let's see if the Pythagorean theorem is working as expected here. Plugging in the numbers, we get the square root of 12 squared plus 5 squared, which is the square root of 169, which equals 13. So this is our original triangle. We now increase x from 12 to 16, like this. That changes our equation to this. Notice how we're squaring 16 instead of 12 now. Clearly, 16 times 16 is larger than 12 times 12. Because of this, our final number under the square root sign is larger. Now, remembering when we discussed square roots in part 2, the square root of 281 is the length of a square whose area equals 281. In other words, the length of that square's sides. So, let's compare. What's going to be longer? The length of a square whose area is 169, or one whose area is 281? Hopefully, you see that the square with the area of 281 is going to be larger. This means that we expect the square root of 281 to be larger than the square root of 169, or 13. And in fact, it is. You see here that it is roughly equal to 16.8, which is quite a bit larger than 13. Hopefully, you can see from this that increasing either x or y or both, no matter what size triangle we start from, increases the final number under the square root, which in turn makes the calculated hypotenuse larger. I'm hoping that you can now see this effect immediately and will start to recognize it in many other equations. Therefore, we can say that the Pythagorean theorem passes our monotonicity test in general. We're getting there. We've now completed half of our test drives. In the next section, we'll see how h is affected when x and y are both multiplied by the same number. Again, I hope you find these videos to be interesting and helpful. Please keep the comments coming. See you in part 6.